Alright, we're going to look at another example then, and this example is we have the unit square which has these vertices 0, 0, 1, 0, 1, 1 and 0, 1. That's this little square down the bottom, okay, commonly called the unit square because it has area of one square unit. Okay, now we want to find the image of the unit square ABCD. That's ABCD. Find the image of that unit square under this transformation, okay, which is according to this rule here. The x coordinate changes to x plus 4y and the y coordinate changes to 3 times x. Alright, now what we do is we look at each point individually, and so starting with point A, 0, 0, we're going to multiply then using that rule we saw previously. So our transformation T can be written as a matrix 1, 4, 3, 0. And that hasn't come out particularly well on there. Okay, but there should be. I'm just going to correct that. Okay, and you'll want to correct that on your photocopy. That should have a T there. Okay. The transformation T times xy equals our image point x prime y prime. So for our point A, we multiply our transformation matrix T by our original point, but of course when we're multiplying by 0 it becomes unchanged. So the image point remains as 0, 0. So image of A prime is 0, 0. Do the same thing for B, 1, 0. So we've got our transformation matrix T multiplying by 1, 0. 1 times 1 is 1, plus 4 times 0 is 0. So we've got 1. And then for our y coordinate, 3 times 1 is 3. Plus 0 is 3. So it becomes 1, 3. So we can move across to 1 and up 3. That's our image point B prime. And we've got point C, we do the same thing, transformation matrix T times 1, 1. 1, 1's a 1, plus 4 1's. 4, that makes 5, and then 3 1's a 3 for our y coordinate. So we have 5, 3 for our image point C prime. And then finally, the image of D, we go 1 times 0 plus 4 times 1 becomes 4, and 3 times 0 plus 0 times 1 is 0, and so our image point D prime located here is 4, 0. So what we can see then is under this transformation we end up with this parallelogram. Now we will look at further into this particular topic areas and the relationship between the transformation and the area. We can note here that the area is 4 times 3, which is 12 units squared. If you revisit this after we look at the area, you'll understand why that's the case. Okay, let's have a look at the next part here, just briefly. We looked previously at non-singular matrices. Similarly, we can have non-singular linear transformations. Basically, what that means is a linear transformation is non-singular if it is one-to-one. Okay, which means that each of the original points, okay, its source point or the original point, maps into exactly one image point. Okay, so each original point will map into exactly one image point. So an easy test to see if that's the case is if its matrix is non-singular, and you'll remember that a matrix is non-singular if the determinant is not equal to 0. Okay, so we can do that test. So if the transformation matrix, the determinant of the transformation matrix is not 0, then the transformation is non-singular. Okay, there's not really a lot in the way of questions that relate to that. It'll be just simply a case of show if a particular matrix is non-singular, or show that this transformation is non-singular, and so you just need to apply this test to it. Okay, and then we'll leave it at that. There's nothing really further with that. All right, so we're going to scroll through and look at linear transformations of lines. Because we can remember that the linear transformations relates to transforming points or lines or curves, if you like. Could be a parabola or a circle, or or figures. Okay, so there's a whole range of different things that we can transform, and we're looking now at transforming linear transformations of lines. And basically, as it says here, the linear transformation of a line results in another line. Okay, some shapes will transform into different shapes, but lines transform into other lines. So let's have a look at this example. Find the image of the line y equals x minus 3 under the transformation t given by this rule. So, in other words, our transformation t multiplying by xy will equal or become our image x prime y prime. What that means is that under the transformation t, the point xy, which lies on the original line, y equals x minus 3, maps or moves to the point x prime y prime, which lies on the image of y equals x minus 3. So there's going to be an image equation, okay, different to the original, where each of the image points lies on. And so, what I've written here is the rearrangement of this matrix equation. Now, you remember that when we are solving for a matrix equation, say A, B equals C, and we want to solve for B, then we need to multiply by the inverse matrix. Okay, and so the inverse times the original becomes the identity matrix, and we're left with B on the left hand side equals A, the inverse of A times C. Well, it's the same here. Okay, what we've got here is T, our transformation matrix, times xy equals x prime y prime, and in order to find xy, or solve for xy, then by multiplying both sides by the transformation matrix T in the correct order, that's what we have here, the transformation matrix of T multiplied by the image point. Okay, so under the inverse transformation, inverse of T, the point x prime y prime, which lies on the image, maps back to the point xy on the original line. So if we applied the inverse transformation to the image, then that would produce back our original point. Okay, going in reverse to that. So we're going to use that fact to find the equation of the image as follows. Okay, so we've got our transformation matrix T, which is 2, 1, 1, 0. The transformation, the inverse transformation then, matrix, which we could find, remember the rule, okay, and by doing that we've got 0, 1, 1, negative 2. So if you can't quite remember, just go back and check how you find the inverse. And so by rearranging, we find that our original xy could be found by applying our inverse matrix of the transformation 0, 1, 1, negative 2 to x prime y prime. So what we can do is from this we can write out these two equations for x and y. In other words, x can be found by going 0 times x prime plus y, 1 times y prime, which simplifies to just x equals y prime. The y, the original y coordinate, can be found by going 1 times x prime plus negative 2 times y prime, and thus we have y equals x prime minus 2 times y prime. Now, this is really important to grasp, so go back over this again and again if you need to. Since x, y, our original point, lies on the original line, that means that y dash, x dash minus 2y dash, these points here, must satisfy the equation of the original line. Okay? Because these points correspond to our original points. Okay? They must satisfy the equation of the original line. So what we do is we replace our x and y in the original equation with these 2 points here, so y prime. So y becomes x prime minus 2y prime, and x becomes y prime. And so we've just replaced, we've substituted those points in here. And thus our equation of the image, by rearranging, becomes x prime minus 3y prime, because we've got minus 2y minus another 1y, minus 3y prime plus 3 equals 0. Okay. You could write it with y prime as a subject. Okay, so in doing that, you're going to have negative 3y prime equals negative x prime minus 3. So y prime equals x prime over 3 minus plus 1. Okay, so that is the equation of the image under the transformation. Okay, this then is our equation of the image, okay, under that transformation T. Alright, so I'm just going to leave it at that, and for the next video we'll look at another example.